Hello, viewers. In today's session, we are going to discuss a very important and conceptual problem from three-dimensional geometry. And here we are going to discuss this problem where we have to find the equation of the plane which passes through these two given points, the point P minus 1 comma 1 comma 1 and the point Q 1 comma minus 1 comma 2, and the plane is perpendicular to this given plane whose equation is 2x minus y plus 2z is equal to 6, right? So here we'll see how we can find out the equation of a plane which contains these 2 points, and it is perpendicular to this given plane. So let us start. So now let us draw a rough diagram. So here the required plane may be taken like this. This is the plane whose equation is to be obtained, and here this plane may be denoted by say pi 1, and this plane pi 1 it contains these 2 points P and Q, right? And this plane pi 1 is given to be perpendicular to this plane, and let us draw this plane like this, right? So here we can denote this plane by pi 2, right? Okay, so now here we'll make use of the concept of direction cosines, right? Suppose the plane pi 1 has the normal vector like this, and let us draw this normal vector as n1. So this is the normal vector n1 to this plane pi 1, and this plane pi 2 has the normal vector like this, right? So here this plane pi 1 is perpendicular to this plane pi 2. So when two planes are perpendicular to each other, then their normal vectors are also perpendicular to each other. So pi 1 perpendicular to pi 2 implies that the normal vector n1 to this plane pi 1 is perpendicular to the normal vector n2 that is to the plane pi 2. So here this angle is 90 degrees, right? So here we'll apply the concept of direction ratios, and let us first write the equation of the plane pi 1 as a times x minus x1 plus b times y minus y1 plus c times z minus z1 is equal to 0. So this is an important concept, right? So the equation of any plane which passes through a point say x1 y1 and z1, the equation of that plane may be written like this, right? And here a b c are the direction ratios of the normal vector, and here we have assumed that the normal vector to this plane pi 1 is the vector n1. So n1 has the direction ratios as a b and c, right? So now this plane pi 1 contains this point P, right? And the plane P has the coordinates minus 1 1 and 1. So this equation must satisfy this point, right? So taking x1 y1 z1 as minus 1 1 1, in this equation the equation of the plane pi 1 may be written as a times x plus 1. Here we take x1 as minus 1, so minus and minus becomes plus, and then we have b times y minus 1, and then c times z minus 1, and this is equal to 0, right? So this is our equation number 2. So now this equation also satisfies this point, that is point q, that is 1 minus 1 and 2. So this point q also lies on this plane pi 1. So this point also satisfies this equation too. So let us write for x, y and z as 1 minus 1 and 2. So we have now the equation a times 1 plus 1, then we have b times here we have y is equal to minus 1, and then we have c times 2 minus 1. So z is equal to 2. So now we have an equation containing a, b, c, where a, b, c are the direction ratios of the normal vector n1 to this plane pi 1. So we have now 2 times a, then we have minus 2b, and here we have simply c, right? So now we have this equation in a, b and c. Now let us form another equation in a, b, c by using the concept of direction ratios, right? Now see, the direction ratios of the normal vector n1 are a, b, c, and the direction ratios of the normal vector n2 to this plane pi 2 may be written with the help of the equation of this plane pi 2. So here the coefficients of x, y and z gives us the direction ratios of the normal vector n2. So we have the direction ratios of vector n2 as 2, minus 1 and 2. So here we have 2, here we have minus 1, and here we have 2, right? Now the plane pi 1 is perpendicular to pi 2. So the normal vector n1 is perpendicular to n2, right? So now let us apply the condition for perpendicularity of two vectors. So when two vectors are perpendicular and they have the direction ratios as a1, b1, c1 and a2, b2, c2, then the condition for perpendicularity of two vectors is given by a1 times a2 plus b1 times b2, and then we have c1 times c2 is equal to 0. So here a1, b1, c1 may be taken as a, b, c, and then a2, b2, c2 may be taken as 2, minus 1 and 2. Now applying this condition, we have a times 2, and then we have b times minus 1, and then we have c times 2, and this is equal to 0. So we can now write here 2a, then we have minus b, and then we have 2c is equal to 0. So this is our equation number 4, right? So now we have two equations in a, b and c, and now we have to solve these two equations in a, b and c. So now to solve these two equations, the usual practice is to make use of the method of uh, that is cross multiplication, right? But here we are going to use the method of elimination. So we'll select any one of these variables and we'll try to eliminate that variable from these two equations. So here we can select a as the variable to be eliminated. So let us subtract these two equations. So subtracting equation 4 from equation 3, we have here the sign minus 1, here we have plus, and then we have minus, and these two terms 2a and minus 2a get cancelled, and here we have minus 2b plus b, that is simply minus b, and c minus 2c is minus c, and we have minus b minus c equal to 0. So we can now write here minus b is equal to c, right? So now here let us introduce a scalar, say lambda, which is a real number, right? So we can take minus b is equal to c is equal to lambda. So the purpose of introducing this scalar lambda is to express a, b and c in terms of lambda. And remember here lambda is not equal to 0, that is it is a non-zero, right? So from here we can obtain minus b is equal to lambda, so that b is equal to minus lambda, and then c is equal to lambda, right? So now substituting the values of b and c in any of these two equations, we can express the value of a in terms of lambda. So let us substitute the values of b and c in equation 3. So we have now 2a, and then here we have minus 2, and b is minus lambda, then c is lambda, and we have 2a plus 2 lambda plus lambda is equal to 0. So 2a plus 3 lambda is equal to 0. So we can now write 2a is equal to minus 3 lambda. So a is equal to minus 3 lambda over 2. So now we have the values of a, b and c in terms of lambda. So now the equation of this plane pi 1 can easily be obtained by substituting the values of a, b and c in equation 2. So here we have a is minus 3 lambda over 2, and here we have x plus 1, b is minus lambda, and here we have y minus 1, and c is lambda. So we have lambda times z minus 1 is equal to 0, right? Now see here lambda appears in all these three terms, right? So if we take lambda as common, so we have minus 3 over 2. Here we have x plus 1, then we have minus y minus 1, and here we have z minus 1 is equal to 0. Now this scalar or this real number lambda is not equal to 0. So this expression has to be equal to 0. So we have minus 3 by 2 x plus 1, then we have minus y minus 1, and then we have z minus 1 is equal to 0, right? So let us now here arrange the terms by multiplying throughout by 2, so that we can easily get rid of this factor 2. So we have minus 3x plus 1, and then here we have 2 times y minus 1, and here we have 2 times z minus 1 is equal to 0. So now we have minus 3x minus 3 minus 2y plus 2, and then we have 2z minus 2 is equal to 0. So let us simplify. So we have minus 3x minus 2y, and then we have 2z, and here we have this 2 and this 2 get cancelled, and we have minus 3 is equal to 0. So now let us multiply this equation both sides by negative 1. So here we have 3x, then we have plus 2y, then we have minus 2z, and here we have plus 3 is equal to 0, right? So this is the required equation of the plane pi 1, which contains these 2 points P and Q, and this plane is perpendicular to this plane pi 2, right? And we can see that this equation is of this form, that is ax plus by plus cz plus d is equal to 0, because the equation of any plane can be expressed by this equation of this form: ax plus by plus cz plus d is equal to 0. So this is a first degree equation in x, y, and z. And a, b, c gives us the direction ratios of the normal vector to the plane pi 1. So here the coefficients of x, y, and z are 3, and then we have 2 and minus 2. So the direction ratios of the normal vector n1 are given by 3 comma minus 3 comma 2 comma minus 2. Hello viewers, in today's session we are going to discuss another important problem from three-dimensional geometry, and here we are going to find out the equation of a plane which passes through this point, that is 4 comma 7 comma minus 7, and the plane contains this line whose equation is x plus 1 over minus 2 is equal to y minus 3 over 3 is equal to z plus 2 over 1. So here the equation of the line is given in symmetric form, right? So let us see how we can find out the equation of the plane where we are given two conditions, that is the plane passes through this point and the plane contains this line. So let us first draw a rough diagram. Suppose this is the plane whose equation is to be obtained. Now this plane may be denoted by the letter pi, and here this plane pi, it contains this point, that is 4 comma 7 comma minus 7, and this plane contains this line. Now see, this line passes through the point that is minus 1, 3 and minus 2, because here we can write the equation of the line like this, that is x minus minus 1 over minus 2, y minus 3 over 3, and z minus minus 2 over 1. See here the equation of a line in symmetric form may be written as x minus x1 over a, y minus y1 over b, and z minus z1 over c. So whenever we are given the equation of a line in this form, then the line passes through this point, that is x1 y1 z1, and the direction ratios of the line are given by a, b, and c. So if we compare this line with this one, then x1 is minus 1, y1 is 3, and z1 is minus 2. So this line passes through this point, minus 1, 3, and minus 2. So let us denote this line by the letter L. So here we have the line L, and since this line L passes through this point, so this point also lies on this plane, that is minus 1, 3, and minus 2. So now we have 2 points lying on this plane pi. So now we can easily write the equation of the plane pi like this, that is a times x minus say x1 plus b times y minus y1 plus c times z minus z1 is equal to 0. So the equation of any plane which passes through a point x1 y1 z1, the equation of the plane can be written like this, where capital A, B, and C are the direction ratios of the normal vector, say n, are given by A, B, and C. So here we have the normal vector like this. So this denotes the normal vector. Now this plane pi contains this line L, therefore this normal vector is perpendicular to this line L, that is vector n is perpendicular to the line L. So now this plane pi passes through these 2 points. So these 2 points must satisfy this equation. So let us first take this point. So substituting this point in this equation, we can now write the equation of the plane pi as a, and here we have x, and x1 is -1. So here we have +1 minus minus plus, then we have b times y minus y1. Y1 is 3. And then we have c and z minus z1. Z1 is -2. So here we have +2. And this is equal to 0. Right? So let us call this equation as equation number 1. Now this plane also passes through this point 4 comma 7 comma -7. So let us substitute here for x, y, and z as 4, 7, and -7. So we have here a, then we have 4 plus 1, then we have b, and y minus 3, y is 7, 7 minus 3, and then we have c, that is here we have c, and z is -7. So -7 plus 2 is equal to 0. So now we have an equation in a, b, and c. So this is 4 plus 1, 5. So here we have 5a. Then 7 minus 3 is 4. So we have 4b. And then 2 minus 7 is -5. So we have -5c is equal to 0. Right? So now using these 2 points and utilizing this equation, we have now obtained an equation in A, B, C. 5a plus 4b minus 5c is equal to 0. So now our aim is to get another equation in A, B, and C using this condition. That is, since this plane pi contains this line L, therefore the normal vector to this plane pi is also perpendicular to this line L. Now the direction ratios of the normal vector are A, B, and C, and the direction ratios of this line L are given by -2, 3, and 1, right? And we know that when two vectors are perpendicular to each other, then we have this condition, that is say a1 a2 plus b1 b2 plus c1 c2 is equal to 0, where a1 b1 c1 are the direction ratios of the first vector, and a2 b2 and c2 are the direction ratios of the second vector, right? So here this normal vector n has the direction ratios A, B, C. So A1, B1, C1 may be taken as capital A, capital B, and capital C, and A2, B2, C2 may be taken as -2, 3, and 1. So utilizing this condition for perpendicularity of two vectors, we can now write A times -2, then we have b times 3, and then we have c times 1 is equal to 0. So now we have here -2a, then we have 3b, and here we have c is equal to 0. So this is our equation number 3. So now we have obtained two equations in A, B, and C, right? And now we have to solve these two equations. So now the usual practice to solve two equations in three variables is the cross multiplication method, but here I will prefer the elimination method. So we'll select any of the three variables here, and then we'll equate the coefficients of that selected variable, and then we'll eliminate the variable by either adding the equations or subtracting the equation. So let us here select this variable, that is variable c. So here we have minus 5c, and here we have simply c. So let us multiply this equation 3 by 5, so that the coefficients of c are equal in both these equations, right? So now multiplying equation 3 by 5, here we have minus 10a, then we have 15b, 5 times 3 is 15, and here we have 5c is equal to 0. So now here we have equation number 4. So now we'll eliminate the variable c from equation 2 and equation 4 by adding equation 2 and equation 4, right? So here when we add equation 2 and 4, then here we have 5a, here we have minus 10a. So 5 minus 10 is minus 5a, and here we have 4b, and here we have 15b. So 4 plus 15 is 19b, and here 5 minus 5c and plus 5c. So these two get cancelled, and this is equal to 0. So now we can write minus 5a is equal to minus 19b. Now negative and negative here get cancelled, and we have 5a is equal to 19b. Now let us introduce a scalar here, say lambda, where lambda is not equal to 0, and lambda belongs to the set of real numbers, right? So here we'll take 5a is equal to 19b is equal to lambda, and the purpose of introducing this scalar lambda is to express the values of a, b, and c in terms of lambda. So from here we can now write 5a is equal to lambda. So a is equal to lambda over 5, and from here we have 19b is equal to lambda. So b is lambda over 19. So now a and b are expressed in terms of lambda. So let us substitute the values of a and b either in equation 2 or equation 3 to get the value of c in terms of lambda. So here we'll substitute the values of a and b in equation number 3. So now we have minus 2a, a is lambda over 5. Then we have 3b, so we have 3 lambda over 19, and plus c is equal to 0. So c is now 2 lambda over 5 minus 3 lambda over 19. So taking these two terms to the right hand side. So now here to get the value of c, we have to solve this expression, and here we can take the LCM. So we have the LCM of 5 and 19 as 95, and now taking the cross multiplication, we have 19 times 2 is 38, and then 5 times 3 is 15 lambda. So now 38 lambda minus 15 lambda is equal to 23 lambda over 95. So now the values of a, b, and c are expressed in terms of lambda. So now let us substitute the values of a, b, c in equation 1 to get the equation of this plane pi. So now we have here a is lambda over 5, then we have x plus 1, b is lambda over 19, and y minus 3, and then c is 23 lambda over 95, and here z plus 2 is equal to 0. So now here lambda appears in all these three terms, and lambda is not equal to 0. So we can now write lambda, and then we have 1 over 5 x plus 1, then we have 1 over 19 y minus 3, and then we have 23 over 95 and z plus 2, and here we have 0. So now this scalar lambda is not equal to 0. So this factor has to be equal to 0. So we have 1 over 5 x plus 1, then 1 over 19 y minus 3, and 23 over 95, and z plus 2 is equal to 0. So now let us multiply this equation throughout by 95, so that we can get rid of the denominators here. So now here we have 1 over 5 times 95. So 5 times 19 is 95. So we have 19 times x plus 1, and here we have 19. So 19 times 5 is 95. So here we have 5 times y minus 3, and 95 and 95 get cancelled. So we have here 23 times z plus 2 is equal to 0. So now simplifying this expression, we have now a 19x plus 19, then we have 5y minus 15, and then 23z plus 23 times 2 is 46, and this is equal to 0. So now we have here 19x, then we have plus 5y, and here we have 23z, and here we have 19 minus 15, 19 minus 15, and here we have plus 46. So 19 minus 15 is 4, and 4 plus 46 is 50. So here we have 50, and this is equal to 0. So this is the required equation of this plane pi in Cartesian form, right? So here the form is ax plus by plus cz plus d is equal to 0, because we know that any equation of this form in first degree, that is x, y, and z are in first degree. So ax plus by plus cz plus d is equal to 0. It always represents a plane. So the required equation of this plane which passes through this point 4 comma 7 comma minus 7 and containing this line L is given by 19x plus 5y plus 23z plus 50 is equal to 0. Hello viewers, in today's session we are going to discuss another important and conceptual problem from three-dimensional geometry, and here we are going to discuss this problem where we have to find the equation of a plane which contains this line, that is x plus 3y plus 2z minus 5 is equal to 0, and 2x plus 3y plus z minus 4 is equal to 0. So here we are given the equation of the line as a combination of two planes, right? So here we have two planes, and the combination of these two planes represent a line, and this plane whose equation is to be obtained is parallel to this line, and here the equation of the line is given in symmetric form, right? And later on we'll also modify this equation. Okay, so now here we have to find the equation of a plane which contains this line and which is parallel to this line. Now let us consider the equation of two planes, right? Suppose the first plane is given by say a1x plus b1y plus c1z plus d1 is equal to 0, and the second plane is a2x plus b2y plus c2z plus d2 is equal to 0. Now we are given the equation of these two planes. So let us denote this plane by pi 1 and this plane by pi 2. Now the combination of the equations of two planes gives us a straight line, right? Suppose the plane pi 1 is like this. Here we are drawing a rough diagram. This is the plane pi 1, and the plane pi 2 is suppose like this is our plane pi 2. Now if we take the combination of the equations of two planes like this, then these two planes intersect in a line. So this is the line of intersection of these two planes pi 1 and pi 2, and any point which is common to this plane pi 1 and this plane pi 2 must satisfy the equation of this line. That is this line, all the points which lies on this plane pi 1 and pi 2, and the point should be common to both pi 1 and pi 2, must lie on this line that is given by the line of intersection of these two planes pi 1 and pi 2. So the intersection of any two planes gives us a straight line. So in the given problem, we are given the equations of two planes. So let us denote this plane by pi 1. So pi 1 is x plus 3y plus 2z minus 5 is equal to 0, and pi 2 is 2x plus 3y plus z minus 4 is equal to 0, and the combination of these two planes gives us the line of intersection of these two planes pi 1 and pi 2. So these two equations together represents a line, and the line is the line of intersection of the planes pi 1 and pi 2. So to get the equation of a plane which passes through the line of intersection of pi 1 and pi 2 is given by this equation, that is pi 1 plus lambda pi 2 is equal to 0, right? So this is the equation of a plane which passes through the line of intersection of these two planes pi 1 and pi 2, and here we have to find the equation of the plane containing this line, right, and which is parallel to this line. So let us assume that the equation of the plane say pi is given by pi 1 plus lambda pi 2 is equal to 0, where lambda is some scalar or it is a real number, and we have to now find out the value of this real number lambda. So now our this plane pi is the intersection of these two planes pi 1 and pi 2. So let us draw this plane like this. So this is our plane pi. So now pi 1 is given by this equation. So we have x plus 3y plus 2z minus 5, and here we have lambda, and pi 2 is given by this equation. So we have 2x plus 3y plus z minus 4 is equal to 0. So let us arrange the terms here and collecting the coefficients of x, y and z. So here we have x and here we have 2 lambda x. So we can now write 1 plus 2 lambda, and here we have x, then we have 3 plus 3 lambda, and here we have y, and here we have 2 plus lambda, and here we have z, and the constant term is minus 5 minus 4 lambda is equal to 0. So this is the equation of the plane pi which passes through the line of intersection of these two planes, pi 1 and pi 2. Now this plane pi is parallel to this line, right? So here we can write the equation of this plane, this line, by say in a symmetrical form, that is x minus 2 is equal to, here we have 1 minus y and here we have 3 minus z. So let us slightly modify this equation. So we have x minus 2 over 1, and here we can write y minus 1 over minus 1, and here we have z minus 3 over minus 1. So now we have written this equation in this form, that is x minus x1 over a, y minus y1 over b, and z minus z1 over c. So the direction ratios of this line are given by 1, minus 1 and minus 1. So now this plane pi is parallel to this line. So here we can draw the plane pi, and here we have the line say L. So let us denote this line by L, and here we have the plane pi. So now this plane pi is parallel to the line L. So the normal vector to this plane pi is perpendicular to this line L. So this is the normal vector to this plane pi. Now here the direction ratios of this line L are given by 1, minus 1 and minus 1, and the direction ratios of the normal vector to this plane pi are given by the coefficients of x, y and z in the equation of this plane pi. So the direction ratios of the normal vector n are given by 1 plus 2 lambda, then 3 plus 3 lambda, and 2 plus lambda. And this normal vector n is perpendicular to the line L. So now applying the condition for perpendicularity of two vectors. So here if the direction ratios of the first vector are say a1, b1, c1, and the direction ratios of the second vector are a2, b2 and c2, then if the two vectors are perpendicular, then we have this condition, that is a1, a2 plus b1, b2 plus c1 c2 is equal to 0. So here a1 b1 c1 are 1 minus 1 minus 1, a2 b2 c2 are 1 plus 2 lambda, 3 plus 3 lambda and 2 plus lambda. So here we have 1, then we have 1 plus 2 lambda, then we have b1 as minus 1, and b2 is 3 plus 3 lambda, and then we have c1 is minus 1, and c2 is 2 plus lambda is equal to 0. So now we have a linear equation in lambda. So let us solve this equation for lambda. So we have 2 plus here we have 1 plus 2 lambda, then we have minus 3 minus 3 lambda, and here we have minus 2 minus lambda is equal to 0. So here 2 lambda minus 3 lambda is minus lambda, and minus lambda is minus 2 lambda, and here we have 1 minus 3 is minus 2, and minus 2 it becomes minus 4. So this is minus 2 lambda is equal to 4, and from here lambda is 4 over minus 2. So lambda is equal to minus 2. So the value of lambda is equal to minus 2. Now to get the equation of the plane pi, let us substitute the value of lambda in this equation. So we have x plus 3y plus 2z minus 5, and then we have here lambda is equal to minus 2, and 2x plus 3y plus z minus 4 is equal to 0. So we have x plus 3y plus 2z minus 5 minus 4x minus 6y, and then we have minus 2z plus 8 is equal to 0. So x minus 4x is minus 3x, and 3y minus 6y is minus 3y, and then 2z and plus 2z and minus 2z get cancelled, and here we have minus 5 plus 8 is 3. So here dividing both sides by minus 3, we can now write this equation as x plus y plus here we have minus 1, that is equal to 0. So the equation of the plane containing this line and which is parallel to this line is given by x plus y minus 1 is equal to 0. So the equation of the plane pi which passes through the line of intersection of these two planes pi 1 and pi 2 and parallel to this line is given by x plus y minus 1 is equal to 0. So now here it is important to note that this equation can also be written as x plus y plus 0 z, and here we have minus 1 is equal to 0. So the coefficient of x is 1, coefficient of y is 1, and here this equation is independent of z, so we can here write 0 z, that is the coefficient of z as 0. So now the direction ratios of this normal vector to this plane pi are given by the coefficients of x, y and z. So the direction ratios of the normal vector to this plane pi are given by 1, 1 and 0.